Okay, let's look at the last part of electrochemistry, which are galvanic or voltaic cells. So now with galvanic or voltaic cells, these are spontaneous redox reactions, and we use these spontaneous redox reactions to do work for us. We use them to make electrical energy for us by harnessing the flow of electrons. So here's a fruit battery, okay, but here is more likely what you will see: two beakers separated by a salt bridge going to an external circuit with either a resistor or a voltmeter or an ammeter or something in there. So let's have a look what's going on here. For a reaction to occur spontaneously, you need a strong reducing agent and a strong oxidizing agent. And remember, they'll be on completely opposite ends of the table. One's forward reaction will be positive, one's forward reaction will be negative, and when you add them, when you subtract them, because remember it's EO cathode minus EO anode, you get a big positive value. Okay, so this is the definition. A galvanic or voltaic cell is an electrochemical reaction in which spontaneous, self-sustainable redox reactions occur at the electrodes. And the important part to remember: chemical energy is converted to electrical energy. So how do you know you've got a galvanic cell? What must be set up? There are certain specific conditions that you need to know about for how these cells work. Okay, so the first thing is you have two half cells, and they've each got an electrolyte in them. So whatever the electrolyte is, you then have the metal. The electrode in that electrolyte is the metal of the electrolyte normally. Okay, so electrodes that consist of the metal of the applicable half reaction. So if your electrolyte's copper sulfate, you'll have a copper electrode. If your electrolyte's zinc sulfate, you'll have a zinc electrode. So electrolytes that contain the metal ion of the applicable half reaction. Conducting wires to connect electrodes in the external circuit. Well, that makes sense. If we want a flow of electricity, we need a conductor. And then the last thing is the salt bridge. And they love to ask you in diagrams, what is this? And it's the salt bridge connecting the two half cells. Okay, so the redox reaction in a galvanic cell or a voltaic cell is spontaneous. It happens by itself. It releases energy. It's exothermic, and it just keeps going on its own. It is self-sustainable. The energy change is chemical energy goes to electrical energy, and electrons go from the negative anode to the positive cathode through the external circuit. So now you can imagine if you are losing electrons, okay, you are leaving something behind with a charge. And we don't like things to be charged. Everything likes to be neutral. So how would you make a replacement for those electrons? The short answer is with anions and cations that are in the salt bridge. As the electron goes, a little negatively charged anion will replace it to keep the charge balance. And so everything ends up staying neutral. So when we connect this circuit up, the electrode in the electrolyte and the other electrode in the other electrolyte, and my salt bridge connecting them to ensure neutrality. This reading on your ammeter, or the potential difference between the two cells, is called the cell potential or the cell EMF, and we write it as that EO cell. Okay, let's talk a little bit about the salt bridge. It's usually a glass tube, although last year I made one out of a folded piece of filter paper that had been soaked because I couldn't find a proper salt bridge for sale. So you can use anything that will allow ions to move, and so I used a piece of paper soaked in salt solution. So the glass tube contains the electrolyte. If you've got a real one, your seal ends with cotton wool, and it must have something that doesn't want to react. So you put in a really weak oxidizing and reducing agent so that they can be spectator ions, like for instance potassium, nearly always found as an ion, never as a metal, and nitrates, which just wander around being nice and calm little nitrates normally. Okay, so in the exams they'll say, what's this, the salt bridge, what's its purpose? And the acceptable answers are providing a path for the movement of ions, to complete the circuit, or to ensure electrical neutrality. I always thought of it as ensuring electrical neutrality. So pick any one of these three reasons in the exams if they ask you what's the purpose of the salt bridge. So have a look here. Here is my galvanic cell, and here are the two things, remember, from the table of standard reduction potentials. So here I've got a copper cathode in a copper sulfate solution, and here I've got a zinc anode in a zinc sulfate solution. In my salt bridge, I've got sodium sulfate. So the sulfate ions are the same everywhere. They don't want to react. And the sodium ions don't want to react either. So if you have a look here, copper 2 plus 2 electrons goes to copper, because the zinc is bullying the copper into accepting its electrons, because the zinc wants to be an ion. Okay, so this reaction is plus, 3, 4. If you look on your table, this will say minus, 7, 7. But you can switch the sign if you flip the reaction, but don't do that. That's how the Americans do it. That's where my slide came from. You must do that EO cathode minus EO anode thing from the table. So a minus and a minus will turn this into a plus. And so if you add these together, 3, 4 and 7, 6, you get 1,10 volts. So this, if you've got a light bulb that works on 1 volt, you could actually light the light bulb here if you put it in place of the voltmeter. So my total cell reaction is copper 2 plus zinc goes to zinc 2 plus copper metal. So copper ion plus zinc metal goes to zinc ion plus copper metal. Remember, copper ion and copper metal, not the same. Zinc metal, zinc ion, not the same. When they ask you what is the reducing agent or what is the oxidizing agent, and you're like, oh, I know it's zinc, ask yourself, do I mean zinc or do I mean the zinc ion? Okay, be specific. So zinc is oxidized at the anode and copper is reduced at the cathode. Then the charge changes, the cations and the anions come out of the salt bridge, so everything remains neutral, and it completes the whole circuit, so the charge flows and does work in the external circuit. Now whenever we get one of these galvanic cells, we can't be busy drawing the pictures all the time, so we have this thing called cell notation, and it's the chemistry abbreviation, so you know what's going on in the electrolytic cell. So have a look here. We've got vertical lines in this. Look, check, this one looks like your parallel line thingy. Okay, so you write everything about the anode on the left and everything about the cathode on the right, and they are separated by the double line, and the double line represents the salt bridge. So you write the name of the anode and its state symbol, and then you write the name of the anode electrolyte in aqueous solution, so like copper 2 plus sort of thing. Okay, and then on the other side, can you see it's like a mirror? There's an electrolyte close to the salt bridge and there's an electrolyte close to the salt bridge. Okay, so the anode electrolyte on the left, the cathode electrolyte on the right, and then after a solid line, the name of the cathode. So see here, for that reaction we were just looking at, the zinc plus the copper ions go to copper plus the zinc ions. Remember, look here, anode on the left, cathode on the right. So zinc to zinc 2 plus, here's my zinc metal making zinc 2 plus ions. There are my salt bridge. Here are my copper 2 plus ions, and there's my copper solid. So it's like the salt bridge is like sort of a mirror. So solid, aqueous, aqueous, solid. Okay, whoops, I forgot the state symbols on the zinc side. Please try to remember, put your state symbols in. Zinc solid, zinc 2 plus aqueous. So the oxidation is on the left, the anode. Oxidation on the left at the anode. Reduction on the right. Maybe it's easier to remember reduction on the right. Okay, so remember that in your table, the reactions are written according to the ability to gain electrons, which is the reduction potential. So you can help figure out which is being reduced and which is being oxidized by knowing what's on how your table works. And so then obviously if the forward reaction happens easily, the value is positive. Can you see here? Copper 2 plus 2 electrons goes to copper, plus, 3, 4. Zinc 2 plus 2 electrons goes to zinc metal, minus, 7, 6. So this value of minus means that the zinc reaction would rather occur. Okay, so here's my two reactions, okay? This is how they are written in the table. When they ask you for the half reaction, you have to give them the reaction that actually occurs. And this copper one is correct. The copper 2 plus ions are going to copper metal, but this zinc is going back to zinc 2 plus, okay? So zinc is going to be oxidized, and the copper 2 plus ion is going to be reduced. So in order to show you this, if they ask you what is the half reaction that occurs at this electrode, okay? If you want the zinc reaction, it is zinc going to zinc ions. You write the reaction backwards from zinc to zinc 2 plus, okay? And you put the arrow going in the direction of the reaction. Zn solid goes to Zn2 plus aqueous plus 2 electrons. And then the copper reaction is written, and you show it's the forward reaction by putting a single forward arrow. Listen to me nicely. If you put the double arrows, you're going to lose the marks because you have to prove to them you know which reaction is occurring. Is the zinc being oxidized or is the zinc being reduced? You show you have this knowledge with the use of your single arrow when they ask you. Okay, so you can easily find the reaction in the table. Make sure you write it with a single arrow when they ask you, write the oxidation half reaction or write the reduction half reaction. In electrochemistry, this is a new section of the topic. My goodness. Okay, we must maybe talk about this in another video. Okay, let me talk about the standard conditions in another video. Go off and have a look at writing this reaction and working out the EO cell for it from your formula on your data sheet.